Okay, let's start. Today we are going to start talking about submarines. Okay, and ideals. Okay, and we'll do some examples. And I'll give you one homework exercise. It's something that I didn't manage to solve. I'm kidding, but yeah. Okay, so we spoke about rings, right? We said that a ring is right, R with two operations, and we said that, just reminding you, it needs to be a abelian group, right, with regards to addition, and then we need to have closure, right, for multiplication we need closure, right, and we need to be distributive. And then all the other things, identity, inverse, commutative, right? We spoke about also we had a version of not inverse, but not having zero dividers, right? Which is sort of like it's similar to integral domain, right? That it's similar to inversion, but a little bit weaker, right? Okay, so that's just a reminder. We'll leave this on the side for a little bit, okay? So if you remember from subgroups, in subgroup, we needed to have a set that is a subset of the group with the same operation, and it needed to be, the subgroup needed to be a group, okay, under the same operation. So subring is similar, but it's slightly more complicated, specifically because of these options that we have here. I'll list what a subring must be, and then we can talk about it. Maybe just look at example. And a lot of it is just definition, but the definitions are important for later. Okay, so a subring, let's call it, say, S. Okay, so it needs to have the operations, the same operations as R. Okay. By the way, we mark it the same. Okay. You remember we had this thing for subring, for a subgroup. So subring is also, it needs to be, it needs to have the following properties. So it needs to be closed for addition. Actually, it needs to be an abelian grouping itself. Okay, so like a subring needs to be a subgroup. Okay, that's easy. It needs to be closed, and it needs to have the plus identity, or we'll just write it 0. Okay, but that's all included in the fact that it needs to be a subgroup, and even an abelian subgroup, right? Because otherwise the subring won't be a ring. The subring has to be a ring. Now, so right, so it's, you know, instead of writing that, because we're already familiar with it, it's also inversions. So let's just say that that a subring is also an abelian subgroup. Okay.
It doesn't need to be a ring.
Right. But I can write that it needs to be a ring, and then you can deduce that it needs to be there. I just want to be a little bit more specific, okay? right? So it needs to be with regards to addition. Okay, that's easy. And then it just needs to do one more thing in general to be a subring. And then we'll make it more complicated, but it actually just needs to be closed with regards to multiplication. Okay? So to be a subring, you actually don't need much. Okay? But for example, let's say that we had, just take an example just to show like what you're allowed to do and what you're not allowed to do. Okay, so let's take an example, or e.g. Let's take an example that we had, say, a ring with identity. Okay, and soon I'll give an example of when this works and when this doesn't work. So I can define a subring for this ring, and then it doesn't need to be with identity or with anything. So long as it's closed for multiplication, it's fine. Okay? But if I say that I have a subring with identity, okay? If I say about something that it's a subring with identity, then it must be a subring with the same identity as the ring. Okay? I can't have a ring, like, for example, I can't have a ring without identity, and then a subring of that ring and say that that's a subring with identity, because the ring doesn't have an identity. Okay? And it's just the terminology that we use, because we'll see that actually the whole reason that we're going through this is eventually to get to quotient rings, okay, which are similar to quotient groups, and then we'll have the first isomorphism theorem for rings, okay? So the terminology here is very important because, for example, let's imagine that we had matrices of the form, I don't know, like xy 0, 0, okay? Xy, say, are over the reals, okay? So, and let's say that multiplication is just like element-wise, okay? Just to make it easy, okay? So the identity, and say that this is a ring with identity, okay? So the identity would obviously be 1, 1, 0, 0, right? That would be the identity for this. Now, let's say that we had that a subring would be this, would be x0, 0, 0, okay? Which is a subring of this, right? It still works the same.
Why is that then identity?
Why? I said that the multiplication is element-wise.
Okay.
Okay?
You define it.
I just defined it as something simple. Right, like, let's make it like this. Define, okay? So I would like to define a subring of this form. Obviously, it's a subset, okay? And if you check, you'll see that it's closed under with regards to multiplication. Just because the multiplication is very simple, it's just a subring. But this is no longer in the subring group, right? Because a subring, this has to be a 0.
Yeah.
But I can define another identity that would look like this, right?
Okay.
This would be an identity if this was just a ring, and this would be the identity. But it's not the same identity as the ring, and so I cannot say that this is a subring with identity. Okay? I can still say that it's a subring, but I can't say that it's a subring with identity, and that's important.
But isn't the first row identity can function as an identity for the lower row?
Yeah, but it's not part of the.
Ah,
It's not part of the subset, right? Because the subset was defined with just one non-zero element. Yes. Like if I would define, say, if I would go and say, okay, that the subset, the subring is actually this, right? Say union with this, but this would also be a problem because then I would actually maybe be able to generate like a whole lot of things from here, right? With the abelian groups, it may get a little bit more complicated. Need to see if it's even closed for everything that we need. Okay, so this is a simple structure. Okay, and we basically talked about terminology. But now let's actually look at something more interesting. So we want to look at something called an ideal. Now, for the ideal, we actually, what we do is we make this closure more strict, okay? So how is it more strict? I mean, what's closed with regards to multiplication of the subring would mean that if I've got A, B that are in the subring, right, then A times B has to belong to the subring, right? That's the condition. Yeah.
Mm-hmm.
Ideals, maybe I'll take another marker so that I can, so this would be just a standard subring. Okay. And an ideal is slightly more strict. An ideal says the following. Okay. And remember that everything that we're doing is towards these quotient rings. Okay, it's very similar to how we started with like subgroups, and when we got to like normal subgroups, right? Which we could then, from the normal subgroups, we could actually create those quotient groups. So the closure for ideals is as follows. It says that if A is in S, but B is in R, in the ring, okay? And AB is in S, okay?
So the subring is like what? Some kind of
Okay,
projector
I'll draw it.
it's on the big ring, so it always brings elements within the
Yeah, I guess you can think of it as a projection in some sense, maybe, yeah. Let's say we'll just do it pictorially, and we're gonna, I think, keep using this today. Say that this is R, and this is S. Okay? And then what we say is that if we're doing the subring, right, and this is AB, right, then this is the subring, okay? But for ideal, we'll just follow the same. B would be any point in here, and it's enough that just one of the points is in S, the multiplication maps back to S. Okay. Now you could make a distinction, and we're not gonna. I'm just gonna say it now, and then we're going to just ignore it. But you could make a distinction of right and left ideals. When you have non-commutating rings, right, then you could say that like you could do like a left ideal would be that I think a left ideal is when B, like this is a right ideal if it's not commutative, and left ideal if it's BA. But we're gonna assume that we're always I mean, and you don't actually, I think you don't actually have to have commutation in order for having both left and right ideals. So you can create structures that are not commutative, but you do have both sides of the ideals. When we talk about ideals, we'll generally speak about like a two-way ideal.
Well, can you highlight the difference between ideals and normal subgroups? Because on the surface they look the same. I guess the one is defined over groups and this is defined over rings.
Yeah, we said that a normal subgroup is one where it's a subgroup where the
Especially when you multiply something from the group, you remain.
yeah, it's
inside
also
the-
something to do with right and left, right?
Right, it's something
So-
that looks very similar. So I wonder if.
Yeah, well, so ideals technically also partition like the set, the same way as normal subgroups partition like the set of the group.
Okay.
Okay, I think that's and you're going to see that we're going to get to at the end of today, but we'll continue it next week. We'll get to what's called principal ideals, which are similar to cyclic subgroups. Okay, so you generate them like they've got a generator. Okay, and those are actually the types of subrings that we're going to be most interested in. The principal, the ideals. I think that perhaps you can get away with certain types of ideals and generate the quotient groups, but I think that it would tend to be more complicated, whereas with principal ideals you could always generate quotient groups. Okay. So that's the direction. Okay. Now, let's talk about, so now we're going to ideals, right? We'll erase that, even though we'll probably have to rewrite, like redo some of this a bit later. Let's talk about trivial ideals, okay? So, if I've got R, right, and we'll just assume that R is a ring, plus and for plus and multiplications. So R is an ideal, right? I mean, you can check it, right? We can always the addition part we're going to put aside. Because for most cases, it's pretty trivial. But you can see that the multiplication, obviously, from R into R by definition, right? Because it's the whole ring, so obviously it's also an ideal. And also 0. Okay, so they're both
Right, if you have 0.
just 0, right? Because 0 times anything is 0, so you get an ideal.
Yeah, so you're talking about R like real, right?
No. R is
the
this.
ring.
It's just the ring. Yeah.
So why do
Not
you assume...
if when I write R is real, so I usually write it with
Right, so why do you assume that there is 0 exists?
0 exists in the ring always because it's an abelian.
It's the identity of the right.
Yeah.
So
Okay, this is usually called the trivial ideal. Like this is called trivial, and I don't know if this has a name, but there is something called, when you talk about proper ideal, you would usually refer to an ideal that's not the trivial ones. Okay.
Do you happen to know what is the reason for the name ideal? Is it because of some Platonian?
Well, I think it's actually more recent. I think it has something to do, and maybe I'll look into it for next lesson. It has something to do with being able to uniquely factorize the elements. Each element of the ideal is uniquely factorizable, whereas if it's not an ideal, then it's not uniquely factorizable. Like you can find different factorizations, and I think it basically just causes these like problems with, like, the structure is problematic and you can't build on it as easily. But it's got to do, the basic thing has to do with factorization. Maybe that's where, you know, ideal.
Why do the rationals are called rationals? Like, I don't know.
No, that
If
has
you
some
have, like,
consideration.
Okay, that's guys.
If you have a big ring and there are like two sub-rings, let's say, and then you have a B which is in R, neither in S1 and S2, right? And
Well, I mean, you can have, right? I mean, like, you'd always have, if you had two ideals, right? They always
have to intersect.
have to intersect on a
right,
zero,
right,
right? Obviously.
Right.
So you can have a point here that's like in R and not in I and not in J.
Right. So this is not, so in that's the thing in rings, that like all of them, all the sub rings actually have to intersect at the same.
Because they're subgroups, right? So they have to.
So it's when you said factorization, it didn't mean in terms of, because you can't really.
So I think factorization is it's like what we would call, in some sense, prime factorization, but I think it could get more complicated when you're talking about abstract rings and subrings, and so I'm not sure that it's going to be so easy to dive into this abstract algebra.
I thought,
but I'll try and
I'll
try and find like maybe a simple example for next time,
Sure.
that we can see that there's this basis for factorization. Okay. You'll remind me.
Yeah.
Okay. All right.
I only understand with examples.
No, it's fine. I get
How
it.
is just one is also an ideal?
So one on its own cannot be an ideal.
Why?
But we can talk, if one exists in the ring, then you need one and zero. At least the ideal, because it needs to be it needs to be an abelian subgroup, right?
Okay.
One is not a group.
Huh? One on its own is not.
When you multiply
What is
one by something, then you get the something.
Oh, right.
It's not closed.
Yeah, right. You're right.
Yeah. But then you'd have a like, because if you have 0 and 1, then you need some sort of
That's
modulo in order
Yeah.
to like have closure, right? Like, you're not gonna have closure with one by itself. Okay, so let's look at some examples of subrings and ideals. Okay, and then we'll do something slightly more interesting. Okay, let's look at the reals and Z. Okay, so we'll look at Z. Okay, we'll say that Z is a subring. Okay, but we'll ask if Z is an ideal. Okay. All right. So first of all, it's a subring, right? Because it has. We know that it's a group, right? It's got the 0. It's got. Wait a sec. It's closed under addition and multiplication. Right? But it doesn't have. It's got the additive inverses. It doesn't. But it doesn't have. It's what we call an integral domain, because it doesn't have what's it called, the zero dividers, right? But now let's let's take, say, choose any element in Z, right? 3, right? And now, in order for this to be an ideal, we need to be able to multiply it by any element in R and map back to Z. But obviously, you know, I mean, I don't even need to work hard. I can just multiply it by half. Right? The number already not in Z. So it's a subring, not an ideal. Okay, let's do something. Let's do another example. Let's take NZ, all right? Or I think maybe we wrote it. NZ, right? NZ would be like 0 n minus n, right? And then and we'll try and do this, okay? So again, right, we've got, I mean, it's got the 0, it's a subgroup, and now, let's see what happens when I multiply something from here by something from here, right? So I would get n times z, right? Times z, right? Z would be, or z1, z2, whatever. Right? z1, z2 are in z, right? Which is a ring, so z1 times z2 is in z, so then we get again nz. Okay, so that is an ideal. Okay. And it's actually, notice that I only checked it on one side, right? Technically I would need to also check it on the other side, right? If I want to say that it's not just a one-sided ideal, then that's all.
Yeah,
But because everything is commutative here, it's fine. Okay, let's look at, I don't know if this example is so interesting. Okay, let's look at it anyway. Look at Z4 times Z4. Z4 is modulo 4, 0, 1, 2, 3, right? So we look at Z4 by Z4, and let's look at this would be the ring, okay? And then let's look at the following ideal, or the following, sorry, not ideal, the following subring of just that the two are the same. Okay, so 0, 0, 1, 1, 2, 2, 3, 3. I mean,
you need to define the multiplication and the addition.
right, the multiplication is always element-wise. Addition is obviously element-wise.
Okay.
Okay, we always, in these simple examples, we're not going to make it more complicated. And so obviously, right, that this would behave exactly like Z. And when we multiply it by something from here, for example, I'll multiply 1, 1 by just anything in general, right? Then I'm no longer in I. So it's not an ideal, but it's a subring. But addition obviously doesn't break it. Okay. Let's now look at, today's not going to be too long, right? But this is nearly the last part. We'll also define principal ideals, but we'll do that at the end. Let's look at we'll just do a few, we'll put up a few statements and we'll try and sort of like do a sketch of proof to see why they're true, okay? So, and let's do this interactively, so you guys also help me. So let's imagine that we've got R with identity, okay? So we've got a ring with identity, okay? and we define that I is an ideal. I think that this is how you make an ideal rather than a subgroup. Okay. So then I say that if one, right, the one is a multiplicative identity, belongs to I, then I equals I. Okay. Let's prove it. So I guess if I is an ideal, we already know that it's an abelian group, and we know the following, right? We know that if we take something from I, so we take A that belongs to I, B that belongs to R, and then A, B given I, right?
Yeah,
So
so
if-
if A is 1,
Exactly. So if I choose A equals 1, then I get that B belongs to I, but B is R, so R equals I. Okay? Simple. Let's do something a little bit more complicated. Let's look at the following. So we'll say that again we've got I think that for this we only need we actually just need to look at two ideals of some R. Okay, so we've got I and J, say like if I take A and B in here, right, then since their sum needs to be both in I and in J, then it remains inside, okay? Now what we want to do is we actually want to take, say, A in here and then R in here and see that it maps to the same place. Or F even, yeah, okay. So if I take A that belongs to I, right? Then AR belongs to I,
but
and if I take A that belongs to J, then AR belongs to J, so it has to belong to the cross. Okay, to intersection. Let's take now instead of
This actually follows
intersection J.
because of that like all submarines will have a trivial intersection like the identity.
the
All submarines in
multiplicative
Right,
identity.
yeah, this is not
Yeah.
necessarily.
Yeah. Let's look at an ideal sum. Okay, so an ideal sum says that I've got A plus B. Okay, I'm actually looking at yeah. I'm looking at A plus B such that A belongs to I and B belongs to J. Okay. So I'm looking at all sums like this, okay, that I take like something from here plus something from here. Okay, and I'm asking if the set of all these sums is also an ideal. Okay. So let's first of all check if it's a group. Okay. So if I take right. Okay, so I take A plus B plus, or maybe we'll do A1 B1 and A2 B2, right?
Right,
And
so it's,
obviously it's A1 plus A2, which belongs to I, plus B1 plus B2 that belongs to J, and we're we're in. Okay, so we've got this closure. Now, right, we need to actually again multiply A plus B by R and still see that it maps, right? But so this is also it's easy, it's AI because of distribution plus BR, and then this belongs to I, and this belongs to J. Okay? Okay. Now, let's look at let's look at what's called, so I've seen it in a few places, but the names are a bit confusing. It's called, what I did now is called an ideal sum. Okay, it's the sum, it's all the sums of elements from ideals. Okay? And it's actually like defined as like x1 plus x2 plus plus xn, where xk belongs to ideal k, and you've got like k ideals. Okay, so it really defines all the sums, because these can also be zeros, so it would define really like all the sums, all the possible sums, right? Including the ideals themselves, like x1 comes from I1 and so forth. So we showed that that's also an ideal. Now we want to look at an ideal product. Now an ideal product, so there are two ways that it's defined, that one of them is an ideal and one of them is not an ideal. Okay, so we'll define it the way that it's an ideal, and then as a homework exercise, you'll take the second definition and show that it's not an ideal. Okay, by just finding a counter example. So we'll define an ideal product as ij. Okay, it's always mapped ij, unfortunately. And we'll define it like this. We'll say that it's actually x1 y1 plus x2 y2 plus xn yn, okay, such that xi belongs to I and yi belongs to j. So it's slightly different. We're looking at two ideals, but we're looking, so right, that the other way of defining it is just xy such that x belongs to I and y belongs to j. And this is not an ideal, okay? Like this is not enough. This set is missing missing something. If you take multiplications, if you take like, right, if you look at this and you take products that x comes from I and y comes from j, okay, then I mean you get some set, but that set is.
Wait, but n is part of the definition.
N is whatever, like it's just n. It's actually any finite sum.
So if you take each will
N equals 1, then you get the second definition.
No, but no. N is any. This is any finite sum of these. Okay.
Right.
This is the definition of this is any finite sums of these. So you generate all the products, but then you also add all the sums of all the products. Any finite sum. N, yeah, N, we could say that N is maybe like, I don't know, if I take the size of these, this would be N, right?
So you need to add
Like this.
n belongs to z or something, I think.
Yeah, and I could say that n equals the size of this. Right? It's like the size of all the products. Okay? Because you should be able to add all the products. It actually doesn't even need to be finite, it just needs to be countable. We're getting into like...
No, I don't. It's not this. But you're saying it can be
Because this also consists of the sum of all the products, all the possible products between the ideals.
But it can be any length of sum, you're saying.
Yeah.
So n isn't there.
No, but any of these could be, yeah, but you could always take like x1 is 0 and x2 is 0 and then you get like smaller sums.
It's like the maximal sum you need.
It's like the maximal sum, but you can always make it smaller by choosing one side to be 0 in those products. You can take 0 plus 0 plus 0 plus 0 plus something for x and y. That would also be part of this. It's just a definition.
Yeah, but it's a strange one. I mean, I don't
Okay,
understand.
fine. But you understand what I'm not the way it's written, but what I'm trying to describe. I'm basically saying if I can create a group of all these xy's, okay, right?
Mm-hmm.
Then now I add all the sums of anything in here.
But if you
So
add,
I
it's
do
supposed-
this plus this, I would get this, and then I'll
Well,
add
it's
this
supposed to
plus
stay in
this.
the group because of closure, no?
No, not necessarily. So that's what you need to. So it won't. For in the general case, it won't. You can find examples where actually like the sum of like this and this will not be in here. You won't be able to describe the sum of two products as a product, basically. Okay. I think intuitively it makes sense that you can't always describe the sum of two products as a product. Okay, but like you need to find a specific example, and we'll like that will be in the homework. But right now we're looking at the set that includes also the sums of the products, so we don't have that problem. Okay, so we're asking, well, we need to show that this is an ideal. Okay? So, by definition, because you've got all the sums, you can see already that it's a subgroup, right? Because you can always, like if you add, say you took x1, y1 plus x2, y2, and you add x3, y3, right, then you can again partition it just like we did before, and you'll get like x1 plus x2 plus x3 from I, and then y1, y2, y3 from J, and again you'll go back to the format that we or you take, you know, technically you don't even need to, you just need to take off the parentheses and use the association, and then it's in there.
The more interesting case is when you have overlaps. Like if you do x1 plus.
Yeah, but you know that that's inside.
Like that, this has to be because of.
Yeah, like-
yeah, it has to be.
Yeah,
Well,
I mean it's inside this definition as well. Because if you do 2, so 2x1 is also in I, right?
yeah.
Okay. So I think that what's really interesting to check is again whether I take something from here, right, and I multiply it by anything from here. Do I go back into this format? And again, I can do it, right, because I can actually take x1, y1, right, plus x2, y2, and we'll just leave it at that. I mean, we can do it for more, right, and then I'll multiply this by r, right, but then I can always like take r with x1 for example, and it would still be in I, right, because r x1 belongs to I, and then again I'll have like I and j. So it'll just be another member of these. Okay. So what we see that bottom line, we see that intersection of two ideals is an ideal, and we see that the sum of two ideals is an ideal, and we see that the product, and I'll say with sums, so it's clear, or with finite sums, is also an ideal. Okay? All right. And for the homework, we need to show example that ij without sums is not an ideal. Okay? And you already showed before that, right? That I is not an ideal. Okay. Last thing for today, just a definition as a preparation for next week. We'll define a principal ideal. So, like we said, principal ideal is a little bit like a cyclic subgroup. Okay. So the definition we will mark it like this. So it's, you remember that the subgroup we had like with the like the triangular brackets. We'll use the normal brackets for principal ideal, and we'll say that it's defined as sorry, I mean it doesn't really matter, but RA such that R belongs to I. Okay? And R is the ring, not the real. Right? R is a ring. This construction defines a subring, and this subring is an ideal, and because it's got a generator, we call it a principal ideal.
What's A? What's A?
A basically belongs to R. Something from R. Okay. Some element from R.
So you're saying RA is an ideal?
I'm saying that if you take the collection of all RAs, then you generate an ideal. Yeah. Let's let's check it. Let's do.
Because A plus A plus A, it's all be.
Yeah. So let's just look. Let's just look at it. So first of all, we know that. Let's just say that R is commutative because we want the two-sided. Okay. So R commutative ring. Okay. Now what do we need? First of all, we need to see, and now, right? We're checking this construction. Okay. So we know that 0 belongs, right? Trivially, it belongs. Now we need to show that we've got all the additive inverses. We've got additive identity. We know that RA belongs to A by definition. And because of that, we know that also minus RA belongs to A, just because we're taking all R's from R and R as the minus. Minus is just the inverse of that, okay? So then we can write, like, since Ra is some element minus Ra, like it's just playing around with association, and we can show that it's got the inverses. So it's an additive group, right? And it's commutative, it's abelian. Then finally, maybe the most important thing to show is the follows: if Ra belongs to A, right? And then let's take S that belongs to R, right? And now let's look at the multiplication of S times Ra, right? But we can actually say that that equals SR times A, and then that belongs to A, right? Because this belongs to R, right? Because R is a real.
What did you say?
I
the
took.
name?
I'm checking close.
Yeah, but what did you say the name of this was?
Ah, sorry. Principal ideal. Principal ideal.
So I think the example you showed before with NZ, it's principal idea.
Yeah. And that's the one we're gonna use also to generate like our quotient rings that we're interested in next time. Right. So this shows us that we've got this closure for multiplication that makes it an ideal, and so the ideal comes from this, and the principal comes from the fact that we can generate it with one generator. That's it. All right. Next week we are going to look at. We're going to actually extend this idea of principal ideal to something called principal ideal domains, and then we'll go from there to quotient rings and the first isomorphism for rings. Okay, and then I think that we're pretty much done with rings. I'm probably going to move on to polynomials. That will be the next topic, and then one of you will need to take over with future topics. All right, thanks.
Thank you.